Thanks for attending and watching today. We have with us Dr. Jeff Volenec, who is a professor of agronomy with Purdue University, a former president of the American Society of Agronomy, and all around excellent individual. So by way of logistics, there will be a poll that will pop up at the end of the presentation. Encourage you to watch for that and fill it out when it comes up. In talking with Jeff, he would like to take questions as we go. However, I was anticipating quite a large group, so I've turned off the ability to unmute yourselves. So please enter those questions into the chat. I will be watching, and I will let Jeff know what questions may arise as you type them in. The snacks, drinks, and restrooms are where you last left them. This is an extension meeting, so I feel like I have to say that. And with that, I believe we'll go ahead and get started. Thank you for presenting today, Dr. Volenec.
Thanks, Hans. I'm pleased to be here. Also co-authored this presentation with Mandana Mirbakish and Sylvie Bruder. They've provided some of the data that I'm going to talk about as we look at how climate impacts plants. So the goals are pretty simple today. I'm going to talk just briefly about the climate, just to give context, get everybody on the same page, and then put those climate change adjustments, put plants in the context of the changing climate, discuss what functions are altered by climate change and how this is ultimately manifested in changes in yield. And along the way, we'll mention a few alterations and interventions that might be used to mitigate or help plants adapt to the climate. So climate factors that are going to impact crop production and the things we're going to talk about today. I'm going to start talking with CO2. That's the driver of some of these climate change impacts and problems. And it will impact yield of some crops, but not all. And we'll talk about who. We're going to talk about temperature and how increased CO2 levels are linked to increases in temperature and also variation in temperature and other things. We're going to talk about a growing season that's going to get longer and have a more variable start and finish to it. And then a little bit about water and how water might mitigate things like drought and whatnot, but also in the big picture, what that means if we start irrigating it en masse in the Corn Belt, places like it. So what's going on in terms of the climate? Well, we know CO2 is going up. Right now it's about 418 parts per million up here. And with that, we see this increase in temperature. These are in the Northern Hemisphere, going up in a linear fashion. So we know the plant's getting warmer because of that. We know it's not because of changes in solar energy. That's the top chart here. The output from the sun's been fairly constant. And that's really good. We don't want to see this change. That would cause all kinds of problems. And then the bottom chart here just shows simply how the increased temperatures have altered one thing. In this case, snow cover in the Northern Hemisphere is gradually going down. And all of these points are 5-year running averages. So we're getting less snow. And we know some of these things are happening. We've heard about them on the news. What does that mean for Indiana in the Midwest? Well, I'm going to talk about Indiana, but these sorts of scenarios are true of most states. So this is with the moderate emission level, sort of in the middle of the pack, not the most extreme, not the most mild emissions of CO2. What's going to happen to Indiana? Where is it going to go from where it's located now to what part of the U.S. is going to be most familiar? Well, with moderate emissions, by 2050, our weather here, climate's going to be similar to what in the summer is going to be mostly like Mississippi, northern Mississippi and Tennessee. With high emissions, it's going to shift a little bit by 2050 over towards Arkansas. But the real dramatic change is with high emissions by 2080, we're going to be down here in the southeast part of Texas. So very much different than what we currently have. So these predictions, let's get down at a more granular level and talk about what they look like relative to things we're familiar with. Here's just adjustments we're going to see by 2090 compared to what we had in 2020. And this again is in the Great Lakes region. I'm going to talk mainly about that region because I'm most familiar with it, but we'll intertwine things from other parts of the country. So we know the temperature is going to go up. In this case, 4 to 5 degrees, a little bit warmer in summer than in winter on average than what we're accustomed to. Precipitation overall in this part of the country may go up a little bit, but the distribution is going to be different, and it's going to be less precipitation in summer, shown here, when compared to winter, and it's going to be higher in winter to counter that. So it's going to be more winter precipitation, less in the summer. Because of that, soil moisture is going to go down in summer. Evapotranspiration is likewise going to go down. That has implications too. And so things are going to be drier, a little more drought in summer, and that's going to affect crop production. We're going to see less runoff because we're less precipitation in summer, more runoff in winter because of the additional precipitation. And some of those events are going to be stronger, more powerful. So that's kind of at the granular level what's going to be happening with some of the climate variables that drive crop production. Recently, there's been an article in the New York Times last month just talking about airlines getting their fuel from corn, growing corn, and they pointed out the impact on water resources. And so we're going to talk a little bit about the water resource issue. But in that article is this nice map showing the aridity index, generally how much drier the Midwest is getting and the Great Plains. This is 1979 to 1991. You can see it's fairly arid in the Great Plains. One would expect that. Indiana, where I live, fairly blue. If you jump forward to 2004 to 2016, the average for that time window, we can see it's a lot more arid, most recently in the Great Plains, a lot drier. And Indiana has gone from blue, which is now up here in Michigan, the lower UP of Michigan, or the lower part of Michigan, to being something more resembling Wisconsin or Iowa. So it's gotten more arid, it's gotten drier. That has implications for crop production, obviously. And if you look at surface temperatures, they're changing. This is a nice map of sort of the array or the rate of change that we've seen. Starts in 1880, goes to 2022. This is compared to the average for the 20th century. So starting in 1900, going to 2000. Okay, so the average is plotted at 0 for that time window. And you can see that earlier, it's been much cooler than it is most recently. And most recently, it's the temperature, the global temperature is really going up at a very high rate. So these things do impact crop growth, production, and some processes, including what I've listed here. Here's just a handful of processes we're going to talk about. We're just setting photosynthesis, dark respiration, stomatal conductance, and leaf temperature in the control setting all at 100 degrees or 100%. Then we're going to put heat stress on the plants. So we've talked about things getting warmer, drought stress, getting drier, and then the combination of those. And really, this is probably the most relevant because we oftentimes, when it gets hot, it also tends to get drier, and drought, in fact, occurs. So with just heat alone, you see that photosynthesis has dropped a little bit, but respiration goes up. Keep in mind that well, if you go back to your beginning biology, we always talked about dark respiration going up, doubling for every 10-degree increase in temperature. Well, it doesn't quite double because the plants have the option to adjust a little bit, but it will go up. Note that when it's hotter, the stomatal conductance goes up to almost threefold. And that's because that's how plants keep cool. They transpire water, and we're going to talk about that in the ramifications of that. So water use goes way up under heat conditions, and leaf temperature goes up. Well, it's warmer, so that's to be expected. Under drought conditions, the stomatal close, the stomates that allow the CO2 into the leaf for photosynthesis close, so it drops way off. Drought causes respiration to curtail just a little bit. There's no stomatal conductance because the stomates have closed to stop losing water, and leaf temperatures have gone up just a little bit. But this troubling scenario is, and the one we're going to face with a lot of climate change, I think, is drought and heat combined. Photosynthetic rates are dropped off. Respiration rates are much higher. No transpiration. Stomates are closed, and leaf temperatures double. So go up quite a bit. Now, why are these things important, these processes? Why am I picking on them? Well, in agriculture, we're interested in growth. And so this is a very simple model that I've used in my class. It's just looking at these processes, photosynthesis minus respiration. That difference is what is left for plants either to grow with it, produce new leaves, new stems, seeds, whatever, or to store, if they don't need the carbohydrates for growth, to store them in some storage organ someplace. The reason why I point this out is that under normal conditions over here, the respiration, dark respiration, consumes about half, 45% of the sugars produced by photosynthesis. That's a whopping amount of carbon sugars going to photosynthesis and not going to growth, not going to stored reserves. So when you see situations like this one where photosynthesis is markedly reduced, respiration is near normal, we have no carbohydrates left for growth, no carbohydrates left to store. In fact, under these conditions, plants will persist by using stored reserves to feed dark respiration. So that combination is pretty tough on plants and reduces yield. So just keep those things in mind as we walk through some of the inner relationships. Now, in general, what's going on with these processes is a function of temperature. This is just a generic plant. We'll parse this out to some other types of plants here in a minute. But if you look, photosynthetic rates are doing pretty good at low temperatures. They peak in this particular scenario around 80 or 85 degrees, and then they start to decline. And they decline pretty quick at really high temperatures. Dark respiration, the blue line, low at low temperatures, increases slowly over time. These lines eventually will cross with respiration still going up. Where those 2 points cross, that's where respiration and photosynthesis equal one another, and there's no net gain in plant dry weight. If temperatures keep going up, respiration will exceed photosynthesis, and the plants start losing weight physically. And so we can measure these things. So really high temperatures means that the plants are losing weight, not gaining weight, and stored reserves are really keeping things alive at this point. So those are things to keep in mind. If you look at real plants, what happens? Well, two different types. We're going to talk about C4 plants, C3 plants. They just have different photosynthetic mechanisms, and we're going to talk about the origin of those mechanisms in just a minute. C3 plants, from an evolutionary standpoint, are older. C4 plants are recent entries into the plant world, and we'll show you that in a second. Note that C4 plants, as CO2 levels go up, right now we're at about 400, they saturate. Their photosynthetic rates saturate at about 200 part per million CO2. We're at 400. So any increase in CO2 from 200 on up is not going to benefit the photosynthetic rate of C4 plants. It's not going to benefit yield. Remember, photosynthesis minus respiration. So photosynthesis is the starting point. So as CO2 goes up in C4 plants, we don't benefit in terms of acquiring more carbon. C3 plants, however, keep going up as CO2 levels keep going up. And they do respond. There's this sort of CO2 fertilization effect. Well, they do respond to higher CO2 levels. Temperature responses are different for these plants as well. C4 plants have grow much better at high temperatures. In fact, C4 plants will not grow at 10 degrees C, which is 50 Fahrenheit. Remember, for corn, which is a C4 plant, the base temperature is 10 degrees C, and we don't count growing degree days at temperatures lower than that. They don't accumulate them, but they do grow well at temperatures of around 90 degrees up here. C3 plants, cool season plants, we call them, things like alfalfa, soybeans, clovers, your most cool season grasses you use for turf. Very wide photosynthetic optimum at low temperatures, but then at higher temperatures drops off precipitously. So they're not adapted to high temperatures that we're going to encounter with climate change. So two big differences in these types of plants. Now, where did these differences come from? Let's go back in the historic record. Here's current time, going back in time 600 million years. We've got pretty good records on what, starting then, about what the CO2 levels were, what the O2 levels were. And this is when C3 plants were coming on board and dominating the landscape. And you can see that the O2 levels were reasonably low. Here's current levels, so they were lower than currently. CO2 levels were much higher than they are now. So we're kind of going back in time to how C3 plants evolved. As they started photosynthesizing and using all this CO2, they drove CO2 levels down and O2 levels went up. Remember, here's the balanced equation for photosynthesis that consumes CO2, makes sugar, and gives off O2. So huge jump in O2, reduction in CO2, and this caused some photosynthetic problems for C3 plants because they photorespire. We won't go into that, but under these conditions where high O2 levels exist, low CO2 levels exist, that we had at this point in time, the photosynthetic efficiency of C3 plants drops off. And so they were struggling, and that put pressure on evolution to come up with C4 plants that don't photorespire and can use these low CO2 levels. And so remember, 200 parts per million. So C4 plants are very adapted to these situations. The other advantage is that they also are adapted to higher temperatures. So C4 photosynthesis itself evolved from C3 photosynthesis more than 60 times around the globe as these environmental changes were occurring, and some of those places are located here, the origin of C4 species. So very different photosynthetic mechanisms, and that has ramifications going forward as we go into a climate where we have more CO2 and things are warmer. Now, how can we study future climates? Well, one approach has been to use these free air CO2 exchange. They're called FACE systems. This was a global network that set up big ring structures, see it here, where CO2 is being monitored in the middle, and there's little pipes and valves sticking up here all the way around it. And the goal is to monitor prevailing CO2 in the middle of the ring and keep it at a high level, at an elevated level that we're likely to encounter in the future. And you can see the mapping here, when they turn on the fumigation, that means when they turn on the CO2 at a bit before 6 in the morning, and all these valves open up, and the regulation of those valves is tightly controlled. You can see in this case, we got about 550 parts per million CO2. Remember, currently we're at 417. And when this work was done, the concentration was below 400. At night, the valves turn off. We go back to prevailing CO2 levels. So that's how we fertilized in a field setting crops in the field with CO2. And this was necessary because a lot of work was done in growth chambers and greenhouses, but we got much larger yield responses than we knew were possible. So they were filled with artifacts. So these were very expensive to run. There was a network globally, as I said, that worked on most major crops. We'll look at some of those here in a few minutes. Duration was 3 to 5 years, very expensive, a lot of CO2 to purchase. One thing that does occur with this is that the elevated CO2 inside the ring causes the plants to partially close the pores in their leaves, the stomata. And that prevents transpiration or slows transpiration, and these plants warm up. And you can see it in this photograph right here. You can see the prevailing field, the bulk field around it is cool. It's very dark. It's at 30 degrees C. But inside the ring, where the stomates are partially closed, it goes up to into the 32, 33, 34 centigrade range. We'll come back to the ramifications of that in just a few minutes, but heat stress is one of the issues that this causes. So what kind of yield data do you get from studies like this? Well, we've got maize and sorghum at the top. Remember, these are C4 plants. They do not respond to elevated CO2. And there weren't many studies done because we knew this, but these were check studies. We just needed to verify what we knew from greenhouse and growth chamber studies. And this is the ratio of elevated to ambient CO2. What did the yield do? And a value of 1 means it was identical inside that ring with high CO2, outside the ring with ambient levels. And you can see the numbers, you couldn't make them up to be any more perfect. They're right at 1. okay? And there's no impact because we wouldn't expect it based on their physiology. Soybeans, C3. Okay, 2 studies were done. These were both done at Illinois. A 15% increase in yield, that ratio. It's almost significant. If this didn't cross the number value of 1, numerical value of 1, it'd be significant. So it's almost significant, but not statistically significant. But I think that if we were to run another study or two, this certainly would be significant. So soybeans tends to respond to elevated CO2. Rice and wheat do respond. You can see that a 12% increase in yield for rice from 8 studies, 13% increase in yield for wheat. And there's the confidence intervals. They don't span 1.00, so they're significant. Another thing about the wheat study was that they broke out some of the rows in those plots when they did these and put on different levels of nitrogen. And this shows the need to have adequate end fertilization to get the response. Here we see that these are not significant. They span 1 when the end levels are low. Here with the highest end level, it's a 15% increase in yield that was significant. So end management and things like that might change a bit going forward in a changing climate. We'll talk about that here in just a minute. Here's some of the impact, some of the data from our graduate student looking at the yield responses of a broader array of C3 plants. All of the numbers 1 through 6 are all C3s. Maize is a control. And this is a meta-analysis, so the data looks a little bit different. No response, the things would overlap with this vertical line right here. And you can see that for the maize, the air bars overlap right there with the line, so it's not different than plants growing in ambient CO2. But all of the other C3 plants do respond. Their air bars do not overlap. And the most responsive right here, sugar beet, but there's just 1 study for it. So it's not a lot of confidence in that. But all of these here respond as normal. Now, what I want to do is draw your attention to the corn data. The corn data can be broken out into 2 years. This work was done in Germany. 1 year was wet, 1 year was dry, and we got different responses. In the wet year, we got the anticipated response where the results were right at or overlapped with the value of 0, so no response. The ambient and elevated CO2 levels gave us the same yields for maize. But in the dry year, you can see that the air bar doesn't overlap, and it got a significantly higher yield for maize under elevated CO2 when compared to ambient in that dry year. And that is because these plants, remember, they partially close their stomates. And it is very likely that in that dry year, the plants closed their stomates, conserved some water, and came out with slightly higher yields. But this is an unusual response. So the elevated CO2 is going to change water relations as we go forward in some of these C4 plants, and it may be of some benefit. Let's see, and you can see again inside the ring the partial stomata closure that might be conserving water for these corn plants. Now, let's go back to the nitrogen story for just a bit, and we're going to look at yield of wheat on the top, rice on the bottom. These were grown at 4 different end levels in both sets of studies. In this case, the typical nitrogen rate would be this N2 for the wheat, the N2 for the rice. And so that that doesn't have a little box and no air bars because that represents the line. This is the typical response that we would get. And the top data for ambient conditions, the bottom data for elevated CO2 conditions. And so let's look at them separately. First, wheat with ambient CO2. The response is what you'd get. Low N level, okay, lower N, numerically slightly lower than here, which is the typical N rate under ambient conditions. And as we increase N to higher levels under ambient condition, yields go up. Under elevated conditions, what do you see? Well, you see the box for the N2 moves over a bit, so it's slightly higher, but still is not different than the previous value up here. But we do see a response with N2. Okay, it represents this spot right here on the line. So the levels, the yield with elevated CO2 goes up for these plants given the normal amount of N, and we know that. If you give them even more N, the yields go even further than what we would see. So you can see that adding N in a future climate with high CO2 may be beneficial for these C3 plants and actually may be needed to optimize yield. In case of rice, the same basic story. Again, the N2 level under ambient conditions is the control right here. You see that under lower N levels, the yields are lower. And in this case, N3 and N4 did not increase yield under ambient conditions. But if you go and look at elevated CO2 levels, these 4 lines here, all of them leap over the line, and N2, N3, and N4 are all higher yielding. So again, interactions of nutrition are going to occur in future climates, and we need to be paying attention to that. And we may require higher levels of nitrogen and other nutrients to really optimize things. So let's go back and talk just for a second about corn, because while yield won't increase, yield might in fact go down, and that's what the models predict. But here's some real data from Indiana, Illinois, Iowa, and Missouri. What I've done is plot the yield for yields from 2012 to 2022, the statewide yields for these here locations, and then went into the middle of the corn growing regions of these states and looked at the July maximum temperature for each year. And so I plotted just a matter of the yield for, this would be an Iowa point, where the yield was about 88% of the maximum we observed in this decade window. And those plants are growing under about 78 degrees Fahrenheit. So that was the average July maximum temperature, okay? So what happens? Well, there's a broad range here where yields are very good, okay? But we do hit a break point, a tipping point, and that happens to be at about 85 degrees Fahrenheit, above which yields start to decline. And it doesn't matter where you are, it just maps nicely, and the decline is pretty precipitous, and a fairly strong relationship. In fact, yield goes down about 4% for each degree Fahrenheit above 85 degrees. And so you can kind of predict going forward what yields are going to look like if you know what the July temperatures are doing for us. So why does that happen? Well, high daytime temperatures in corn will eventually reduce its photosynthesis. It'll certainly do it in a C3 plant, but it's the hot nights that increase respiration rates. Remember, normally this is about a 45% reduction or use of what's carbon is produced during the day. So 45% of it goes to dark respiration. And the difference is what gets partitioned into growth and grain yield. And so when high temperatures, we got higher respiration rates, the carbon available for growth and grain yield is reduced. Now, other things being equal, water, harvest index and things, growth and yield are better when we got warm days for good photosynthesis, cool nights, and decline when it's hot. So how does one interpret this? What is the magnitude of the implications of this? Well, let's just use that 3.8% reduction in corn yield in Indiana, using Indiana yield information from this year. So we're going to reduce yield 3.8% for every increase above 85 degrees, every degree F. We had 200 bushel yields this year. So this 3.8% reduction times the 200 bushel yield would mean we'd lose about 7.6 bushels per acre for each degree Fahrenheit increase above 85. And if we just project forward, we're predicting about a 5 degrees centigrade increase potentially by 2100. What that would mean? Well, that's a 9 degree Fahrenheit increase. 5 degrees C translates to 9 degrees Fahrenheit. That means we'd have a 68 bushel per acre loss in yield at $404.93 a bushel. I checked earlier this week. It's about a $340 reduction in value for the crop per acre. And we've got 5.4 million acres of corn in Indiana, so it totals up to be about a $1.8 billion loss in just the value of the corn crop. So these are pretty significant implications as temperature goes up and as these plants don't respond to elevated CO2 and give us higher yield. So just keep that in mind. Now, as we look at present day conditions. This is a study done mainly for the Corn Belt, the Midwest. USA, you can see between 2005 and 2015, here's how yield mapped during that period of time. And the average for the region was 151 bushels. If we look at the window of 2090 to 2100 with the high emission scenario, which is the one that we're unfortunately on right now, you can see that because corn can't respond in terms of elevated CO2, there's a pretty negative downside to all of this. Regions that don't grow great corn right now, yields just tank along coastal US. In the southern part of the corn belt, they just go down. And yield is sort of maintained in the cooler parts of the corn belt, but not all that good. And so projected yield in 2090 is just under 100 bushels per acre for the country. So pretty dire predictions. Soybeans, it's a little bit different. Soybeans from 2005 to 2015, you can see this nice green band going across the center of the corn belt. We know that yields are, around 50 bushels per acre, 50 to 60, which is good. The average for the whole region or for the country is about 44. In the high emission scenario, 2090, there is a CO2 fertilization response to soybeans. And so if other things can be adjusted, like water and things, the plants might do okay. It's also an indeterminate crop, which gives it some additional stress adaptation. But you can see that along coastal parts of the country, very poor yields. The center of the country here, again, yields are going to really drop off, but they're going to be compensated for by this region in the northern part of the Corn Belt, where we get even higher yields than we're currently experiencing right now, and yields that exceed 60 bushels per acre. Plants are going to respond to CO2 if there's water, and because they're indeterminate plants, the overall production of soybeans is going to drop just slightly from 44 to 42 bushels per acre. So not all plants are going to respond the same. So what can we do about this? Well, one thing is to look at dark respiration. I want to elevate that as a possible breeding target. It's not really being under consideration right now, but it might be something to think about if we want these plants to be able to adapt to higher temperatures. This happens to be done in ryegrass. It was done in Britain in the 80s, and there's very, very few studies that have followed up on this, but it's probably time to do so. So this is reducing the dark respiratory load. As I said, that normally consumes about 45% of photosynthate. If we get down to 35 or 40%, it would be good. This study, basically, they took the most popular ryegrass grown in Britain, it's called S23, and just selected for one cycle for lower dark respiration rates and created these two other germplasms, GL83, GL112, and then said, okay, plant them in the field, what happens? And you can see that the yields were as good. And in the warmer part, this is again done in Britain, June, July, August, when it's warmer, the yields of these low respiring lines were actually higher, which is promising. So it is plausible that this could work in grain crops. And there's been one study done that I'm aware of recently where they've done this in wheat at Simmet. And it does look like those plants are more tolerant, higher yielding in a warmer environment. So looking at dark respiration may be one way going forward to minimize the effects of climate change on some of these processes that manifest themselves into yield. All right, let's talk a bit about growing seasons and what's happening there. So temperature's changing, the length of the growing season is changing. You can see the map here. It depends where you are, but almost everybody's getting a longer growing season. Indiana, it's going to be about 10, maybe 15 days longer than what it was historically. And the frost-free days are part of the reason why this is happening. They're shown here from 1980, and it's lengthening. Again, compared to the long-term average from 1980 to 2020, early in this 4-decade time frame, we had, the values are negative. Their departure from zero is negative. But more recently, you can see that the days that the growing seasons are getting longer, and most recently in and around the 10-day average amount. And you can see the change in annual unfrozen days here on this map in the Corn Belt is going up to 20, 30, in some cases 40 days where we don't see a freeze. So much longer growing seasons. And that would be viewed as maybe a good thing. But the ends of these growing seasons are getting far more variable, especially in the spring. And here's an example where that's illustrated nicely. This is in Missouri, where a late winter freeze really damaged the crops that were growing there. This happens to be a pasture. And you can see this is pre-freeze, 2nd of April. A week and a half later, the freeze had occurred, and you see that everything that was broke dormancy and had grown was now yellow and dead. And here's a map of those temperatures. And you can see that we're starting right here, it gets above freezing. It stays up close to 60 for almost 2 weeks, and then plummets. And it was hard freeze that killed these plants. So it's this inconsistency that's really causing problems. And 2019 was another year, when 2018, 2019, where again, we had inconsistent springs that led to winter injury, death of both alfalfa and winter wheat systems. So why is that important, and what's happening? Well, part of this is that when we get reasonable snow cover, it buffers temperature changes. In fact, snow is a great insulator. So seasonal variability in snow, here's the percent change in snow cover. And you can see that all the dots are almost red. Everybody, no matter where you live, is losing snow cover. And the bigger the dot, the more the losses. And this again is from 1949 up to 2020. So this is a change during that period. Why is snow important? Well, it acts as an insulator, traps the air. And it's in this table of data from 1916, great work done in Michigan. They just mapped with these dates what the air temperatures were. Started at 30 degrees on January 15th, got down to 2 degrees by, and again, these are Fahrenheit values, by January 30th. If you're looking at just bare soil, no snow, the temperature declines markedly, and you get below 25 Fahrenheit, you're going to start injuring. These are temperatures of the soil 3 inches. You're going to start injuring perennials and winter annuals. So bare soil is not your friend here at all. If you have snow, the temperature barely drops below freezing. And these temperatures are tolerated very well by winter wheat, alfalfa, things like that. Snow and residue on the surface, even though you get into really low air temperatures, the temperature of the soil never gets below 0. So residue is important, snow cover is important, and when we don't have it, we end up having problems. So what's the solution? Well, here's some of our own alfalfa plots that have been damaged by these late spring freezes. Here's some non-dormant alfalfas that are highly productive, and it's the direction that plant breeding is taking alfalfa from very dormant plants to plants that grow back fast after cutting. They are non-dormant in the fall. When you take farmers to look at these plots in the fall, they always want these varieties here, but there's a problem. They start growing very early in the spring. And then in this particular year, we had the same thing that they had in Missouri. There was a hard frost after the plants had started to grow. And you can see the residue here, the non-dormants here and here were really damaged by that freeze because they had started growing and were growing vigorously. The dormant plants here and here had just begun growing and incurred much less damage. They grew back fine. These non-dormants did not. Now, why is that a problem? Well, as we've selected for yield of alfalfa, yield of wheat, we've pushed these plants to start growing earlier in the spring and to be less dormant. So how do you fight, or how do you work against or mitigate the effects of this late spring temperature variability? Well, are we going to go back to more dormant alfalfas, more dormant wheats? If we do, we're going to have to lower our yield expectations, because invariably they will be lower yielding. Okay, let's talk a little bit more about water as we wrap up the discussion. We are looking at precipitation values here, and as I said, total for places like Indiana here in the Midwest going to go up slightly. This is changes in just the 20th century, so we're about 10% more wet in the Midwest than we were 100 years ago. But as I said, that varies with the season. Most of this is coming down in the spring and winter Here's the predictions going forward. And you can see considerably more precipitation, up to 2 more inches in the spring than we've gotten in previous years. This is looking at 1971 to 2000 as a control, and they're predicting what this will look like in 2040. And you see much wetter, particularly in southern Indiana. And this will likely impact when we get things planted in the ground in the Midwest. And as I said, some of this is much more intense in the upper Midwest and in the Northeast. And the downside of that is that these heavy precipitation events leads to more runoff, less infiltration, so less useful for agriculture. Summertime precipitation values, as I indicated, are lower, and here you can see the map of the US. Predictions are to be anywhere from 1, 2 to maybe 3 inches less rain in these states in summer. And that will be in a warmer environment, so there will be more evapotranspiration, more water use by the plants, and the soils will, as a result, dry down. And this goes back to this aridity index that came out of this paper on water use in ethanol fuel production, 1979 to 1991. Here's the data, and Indiana was nicely blue, and there were some dark browns out here in the Great Plains state, but not a lot. Well, that's changed by the time we get to 2004 to 2016. Much drier out here, and the dryness is pushing east. You see that the colors of over Indiana have now shifted up into Michigan and further east. So it's getting more arid here. Soil moistures are declining. Relative humidities are going down, and temperatures are on average going up. And you can see that it's coming in waves in some cases. This is heat wave frequency. The number per year since the 60s has tripled, and the duration of them has also gone up threefold. And you can see the mapping, and this does include lots of places where we grow crops that we care about here in the Midwest. So we're getting hotter temperatures, but also these heat waves. So as a result, if you look at soil moisture levels, anything in red is declining. And that includes much of the Corn Belt, much of the United States, as a matter of fact. It's only Florida that's gaining a little bit of green. Where are we gaining water? It's in northern latitudes here, in Canada, in Russia, places like that. And again, this is a manifestation of reduced summer rainfall, warmer temperatures, where we're using more water, lower relative humidities, and higher runoff rates from these extreme events. An orange value, a value of -3, is frequent severe droughts are occurring. So we're going to have issues with water that we need to contend with. So we've got water. The earth has a lot of water. 75% of the surface is covered with water. The problem is that 97% of the water on the earth is salt water. Plants can't use it. Of the 3% that's fresh water right here, this little green slice, 2/3 of that is in snow and polar ice caps. Can't be used by plants. So there's only 1% of the planet's water that can be used, and most of that's groundwater. A little bit in lakes and rivers, even though I live next to the Great Lakes here. It's just a very small amount that's in those lakes, despite their vastness. So it's time to take a break and just ask the question, how much water do plants need? And I'm going to pick on my favorite plant, alfalfa. And the question's pretty simple. This 1.5 pound bag of alfalfa hay that you can buy to feed your hamsters and gerbils and rabbits, how much water does it take just to grow it? Just to grow it. And I'm making it a multiple choice question. I'm trying to be kind. 10 pounds of water to produce 1.5 pound bag of alfalfa, 50, 100, 1,000, or 2,000. And I've converted it to gallons here, but you know, where on this spectrum do we lie? Anybody care to venture a guess?
We've got 1C at the moment.
Somebody's going for 100 pounds.
We've got a D and a B, a couple Ds.
Well, I think those are all very very good answers. I mean, 50 pounds of water, and I'm using the pounds because I'm going to talk about the ratio of water use to production of the plant dry matter. The answer is 2,000 pounds of water. Okay, that's called the water, and the ratio for alfalfa is 1,500 pounds of water to produce a pound of dry matter. We're going to come back to that. But the point here is that it takes enormous amounts of water for crop production. And I'm picking on alfalfa because it's viewed as a water spender. It takes a lot of water. It's got a long taproot, draws on water resources from deep in the soil profile. And so 2,000 pounds to produce this 1.5 pound bag of alfalfa. That's why agriculture is a rain-fed operation. It takes a lot of water. And it's making the paper finally. Several articles here. One that there's people in Arizona were renting, the state was renting land to people from foreign countries. In this case, this is an article about the Saudis who are growing alfalfa in Saudi to be shipped to Saudi Arabia in container cars. Okay, now when I was a kid, we wouldn't ship alfalfa hay much more than a mile to a neighbor. It just is too bulky and too expensive. You've got the Saudis leasing land in Arizona to grow alfalfa, to put in containers to be shipped halfway around the world. That speaks volumes. They don't have water. Arizona doesn't have much water. And they finally realized that they were shipping water, vast quantities of water to Saudi Arabia in what is a water limited state. But also, here's a recent article a couple weeks ago, came out in the New York Times about jet fuel, growing corn, using it for jet fuel production. But it requires a lot of corn, but it also requires a lot of water. And we're going to talk about this in just a minute. And so there's a heightened awareness about the water use in agriculture, and that's going to also come into focus in a changing climate. This bottom picture here is Lake Mead, record low levels in 2022. This is 2021 when they weren't even the lowest, but it's the same framing. Look at how far the water's dropped. And that's because agriculture upstream from Lake Mead has used a lot, continues to use a lot of water, and the recharge rate into the river has been reduced as well. So water is becoming a critically important resource in agriculture and trade, and it's going to become more important going forward. Critical functions, well, it's turgidity. It's the turgor pressure that gives plants their form, allows them to grow. It's a solvent for things happening, hydrolysis, synthesis of things, minerals, supply nutrients to the plants, and then to cool plants. And I want to touch on this just for a second, because we've talked about it before. You can see these plants right here are under some degree of water stress. This side of the field here is irrigated, and they're blue, and they're much cooler. And there's about a 6 or 8 degree temperature change between these two plant groups, just because the stomates are closed on the left-hand group here. They're not transpiring. They can't keep themselves cool. And that, if you go back to your chemistry books, I know you hated these lectures. I didn't like them. Latent heat of vaporization, you know, when it changes form, when water changes form from liquid to vapor, it takes a lot of energy. This is the number right here. And to put that in perspective for you, to just increase the temperature of water, the heat capacity of water is 1 calorie per gram to go 1 degree C. So if you take water from 0 to 100 degrees centigrade, it takes 100 calories to heat it up. To phase transition then, to go from liquid to vapor, it's 5 times that amount of energy. This is how plants cool themselves. And when water's not available, they heat up immediately. And that's a problem. So again, this is why crops are, you know, agriculture is a rain-fed operation. So let's look at crop water use here and how it relates to grain yield. This is data from Nebraska. It includes rain-fed, the squares, and irrigated areas. You can see that this is a very, very tight relationship. Doesn't matter what the source of water is, rainfall or irrigated, it all lies on the same line. The slope of that line is 32 kilograms of grain is produced per millimeter of water supplied. Okay, so the grain yields are here. And I would simply ask you, where would a more water use efficiency set of these are farms, these are 800 farms, almost 900 farms. Where would a water use efficient farm be? It'd be located out here with really high yields, somewhere where the little pointer is, and a little bit of water use. All these farms end up on the same relationship. There's no outliers, okay? So this is an invariant relationship. This is why breeding for improved water use in corn and other crops is very difficult. This is kind of a fixed issue. So let's talk a little bit about this and water use and scaling crop water use. And we're going to put it in the context of this is a local water project, a LEAP project. They're actually wanting to take water from our county, where I live, to a county 40 miles south of us for an industrial park. And so the context there is what they want to do is we've got a huge reservoir, a nice aquifer under West Lafayette, Indiana. It's called the Taze River. Got a lot of high quality water. And they're going to want to take 100 million gallons of water per day and pipe it down there, kind of like an oil pipeline. So that's the context here. And we'll come back to that number in just a minute. But what I want to do is just look at, well, how much, as we thought about this, how much water is used by the crops in this county? So they're going to take 100 million gallons of water for making microchips and other stuff. What does it take? Is this going to put our crop production at risk, especially if we start irrigating? So we just looked at some papers about how much water is used for soybean production for the grain. And here's the individual papers. The average is just under 2,200 pounds of water per pound of soybean grain. And you can see there's quite a bit of variation in these numbers. For corn, it's more efficient. Less water is needed to produce a pound of grain, and the average is 484, and the values are more consistent. So let's go through just a quick calculation of what this looks like. Here's from how many bushels of corn in Tippecanoe County, Indiana in 2022 for maize, for soybeans. This is from the USDA NASS site. The weight of the bushels. So we can calculate how many pounds of corn grain, how many pounds of soybean, pull out the water that's in those bushel calculations, and you get the dry weight of the corn, the dry weight of the soybean grain. Then you multiply that times the amount of water, how many pounds of water to produce this, how many pounds of water to produce this, and those are the values from the previous slide. And it gives you huge numbers here of water that's needed to produce those. Now, keep in mind that this is assuming all water comes from irrigation, okay? That's not reality, but still we're talking hundreds of billions of gallons or pounds of water. So let's take this one step further. We're going to start right here with pounds of water needed to produce these crops in this county. Look at how many gallons of water that is, divide it by 8.3. So now we're getting to a metric that relates back to the 100 million gallons of water used by this LEAP project. We're talking 45 billion gallons of water for the corn crop, 74 billion gallons of water for the soybean crop for our county. But that's total, so we'll divide it by a 90-day growing season. So you're pulling out, if you combine them both, it's about 1.3 billion gallons per day for 90 days to produce the corn crop and the soybean crop in the county. Now, keep in mind that the context is they're worried about 100 million gallons being piped to Lebanon, Indiana for this LEAP project. But right here, that's trivial compared to what is needed for agriculture in this county. 1.3. So it's 13 times more water is used per day for this 90-day period than they're going to pump to this. So even if we irrigate 10% of the land, which is quite plausible 15, 20, 30 years from now, we're still going to be exceeding what they're going to pump to Lebanon for this industrial park through the LEAP project. And it's a lot of water in both cases. So at least it started a conversation about water resources. But agriculture takes a ton, well, a lot more than a ton of water. It's important. So what happens where they've mismanaged irrigated water? And here's, if you've ever flown over Kansas, you get this view of all these little green circles. Well, those are all the irrigation, the center pivot irrigation systems that are located down here. This is the Ogallala Aquifer here. Anything that's yellow, brown, reddish in color, the darker that is, the more water they're pumping out. And they're under a severe water crisis that this is not sustainable. This recharges at the rate of about an inch per year from rainfall. In the last 15 years, that means it's recharged 15 inches, okay? And they're withdrawing many multiple feet of water per year. Okay, so it's really, really serious depletion. So that's fairly common here. It's fairly common in California. And so agriculture is going to probably go away in those areas because it takes so much water to grow these crops, especially as the climate changes. It puts more pressure on water resources for crop growth in those regions. But another thing is that groundwater removal causes a serious subsiding of land. Something people consider, don't think about. Here's data from California, the Central Valley, the San Joaquin Valley. There's an aquifer here. You can see that the water level is right here, this blue line. When they went into a drought in 2006, they started pumping out of this aquifer. Levels in the aquifer went down, and we have now, thanks to satellites, a very, very precise way of measuring distance or land subsidence. And you can see that the land during this period of time subsided about 100 millimeters, which is 4 inches dropped. So as you pump the water out, the land settles. I love this picture to the right. This shows, again, the same part of California, taken and the measured land subsidence from 1925 to 1977. The land used to be up here, top of this telephone pole, or well up onto this telephone pole. Since they pumped the water out, by 1977, the land surface is down here. So another ramification of pumping groundwater for this purpose. It's a limited resource. It's not refilling quickly. And so we need to really think hard about what climate change how it will interface with our water resources. All right, just a couple of closing thoughts. Climate change is altering important processes in plants. Some, like C4s, will not respond to high CO2 anymore. And so they are at great risk of yield reductions because they can't benefit from the high CO2, but they will suffer from the water shortages and the higher temperatures. Higher temperatures are likely to be an underlying cause for reduction of growth and yield of many, many crop plants, but we might have an option to breed for low dark respiration rates. Water deficit stress will be more widespread in the future and will reduce yields irrespective of photosynthetic mechanism. Irrigation is an option to minimize the impact of climate change, keep plants cool, provide growth, water needed for growth, turgidity, nutrient uptake, but vast amounts of water are needed to support crop growth, and that's problematic. It really is problematic. And I've not seen strong evidence that we can breed for higher water use efficient crops, varieties within a crop. And finally, year-to-year variation in yields will increase going forward because the climate is just inducing some directional changes, but also year-to-year variations that are just sometimes crazy. So anyway, with that, I'm all set. I'm ready to stop sharing, and I'll take any questions if we have some time. Hans?
All right, yeah, we've got time for one, maybe two questions. Go ahead and enter those in the chat if you have them. I'm going to go ahead and start the poll. So please go ahead and fill that out at your leisure, assuming you're on a device that allows you to. And you can do so safely. Seeing nothing in the chat yet, I do have a seed question. There are many negative impacts that you mentioned during your presentation. There is a significant opinion in the agricultural community that with enough research and development, we can overcome any of these issues. What is your perspective on that opinion?
So I think we can do some things. You know, for example, we can irrigate far more efficiently. There are tools, technologies to engineer a solution so we can use that water more wisely. But the vast amount of water that we need to use is still going to be a problem. Can we breed for some things that are going to be better adapted? Yes, maybe with lower respiration rates, but in terms of water use efficiency, there's been a lot of work done on that. And because of I showed that data from Nebraska with all those 859 farms, everybody lies on the same line. It is invariant. and it's unlikely that we're going to be able to get plants to use water much more efficiently. And so it's kind of a mixed answer. Some things yes, but many things not. I mean, I think the best thing to do is to do what we can to mitigate the CO2 emissions and try to get this under control.
Okay. Don't see anything else in the chat, so I did have one question that I wasn't going to ask unless I absolutely had to, and it looks like this is the time. You mentioned your favorite crop is alfalfa, but I didn't hear anything about bird's foot trefoil in your presentation. And if I remember correctly, at one point in time, that's how I learned that that plant existed, was from your class. So I wondered if you had any effects on BFT from climate change.
You know, I would guess it'll track up close to what alfalfa will do. It'll be a C3 plant. I think what I didn't touch on is one thing the trefoil is susceptible to is a lot of diseases. And so as temperature goes up, disease prevalence tends to also go up. I kind of stayed in my lane with the physiology, but bird's foot trefoil is a very famous plant, as you know. It is the only plant I know of, only agronomic crop that has a Muppet named after it, Herbert Birdsfoot. So go look. And Jim Henson's dad, just as an aside, Jim Henson, who came up with the Muppets, his dad was a Birdsfoot trefoil breeder that worked for USDA. Little known fact. All right. Did another question pop up?
We did have one, yes. What about better water infiltration farming practices? So I assume that would refer to soil health and farming practices to better infiltrate water.
Those will be important because I think those more intense rains, if we can do something to just get some of that water, stop it from running off and eroding the soil and get it to infiltrate better, we're going to capture more water, and that's a good thing. So yes, that's certainly something to be considered.
Okay, well, we've run just a couple minutes over the hour, so you're getting some thank yous in the chat for your presentation, Dr. Volenec, and I want to thank you as well. Thank you all for participating today, and happy holidays. Hopefully we'll be able to catch you on a webinar in the next year.
All right, very good. Thank you all.